All right, welcome back. We are jumping into a new chapter here. This is chapter 7. Chapter 7 is almost completely about similar figures. But before you can get into similar figures, we have to do a little reminder about something called proportions. Proportions and ratios. I think we all take for granted the fact that we understand math at a certain level. There's certain things like statistics or probability that we just have ingrained in our minds that we understand, but we forget the fact that this is not just something that is common sense. It's stuff that we have learned and helps us make sense of situations and figure out what options are better or what outcomes are better. So the start thinking part actually brings up that idea. It says the table represents the number of favorable outcomes and losses when it comes to stock purchases in a selected year. In what year did the stockbroker make the best purchases of stocks? Now, I understand that you could be buying a different stock that costs a different amount, or that you might be buying um, different amounts of that stock. But if we're just simply looking at how well did they go over and pick companies based off of whether they're going to be winners or losers, that is what this problem is about. So it says in 1999, the stocks that produced a gain, there were 30 stocks that produced a gain, and there were 20 stocks that produced a loss. Now, if you go over and look at 2002, there were 150 gains, which is pretty darn amazing. And then you had 120 losses. And then in 2006, you had 5 gains and 2 losses. Now, if I went over and talked to a person who didn't understand math and showed them this and said, what was the best year? Let's say I went to my little 5-year-old who's at the Montessori school and said, hey, when did the person do best? He would look at this and go, whoa, 150 is a big number. I studied 150 when I was looking at the 1,000 chain or whatever he says. What he's not realizing is, yes, he had a lot of really good stocks that he picked, a lot of ones that had a gain to them, but he actually had a lot of ones that had a loss as well. So, if you were looking at this, try to think, how could you interpret this to figure out what was the best year? Well, the hint is look at the name of the lesson. We talk about ratios, okay? So one of these things you can do is just look at the ratio of gains to losses, or you can look at the ratio of gains to total. I personally like looking at gains to total because that is what we use when we're looking at probability and stuff like that. So what I'm going to do is I'm going to look at in 1999, they had 30 out of the 50 stocks were ones that were gains. In 2002, 150 out of the, if you put those things together, you get 270 stocks were winners. And then in 2006, 5 out of the 7 stocks were really good. Now, if we looked at this and tried to figure out what percentage of winners were there, 30 over 50, if you put that in your calculator, you get 0.6, which is, you could think of as 60% stocks were gains. If we looked at 150 divided by 270, you get 0.5555. So about 55% of the stocks they picked were winners. And then if you look at the 5 divided by 7 one, that is 71% of the stocks they picked were gains. All right. And when you look at this, as I said, my child, for example, would look at this and say, oh my gosh, look, he did so good. He got 150. 150 is a big number. But they weren't looking at how that related to how many losses there were as well. And when we look at this, you can see technically the best year was in 2006 when 71% of the stocks they picked were gainers. All right. Once again, what we did here to be able to compare these different years is look at ratios. Ratios is a way of comparing two things by division. Sometimes we write it as a fraction, such as 2 to 3. Sometimes we write it like this, 2 to 3. And sometimes you write it like this, 2 to 3. Say, those are 3 different ways that we're talking about the same thing. All right. Now, this is just a little side note. There is a difference between odds and probability. Here's an example. If there were 2 girls and 3 boys, and you are picking randomly, you could talk about the odds of picking a boy would be 2 to 3. Okay? If we were looking at probability, though, you can't say that's 2 over 3, because when we're talking about probability, we're talking about favorable outcomes over total outcomes. Well, how many total outcomes? If 2 girls, 3 boys, there's going to be 5 altogether. So that's actually going to be 0.4, which is 40%. So this is just a small side note because sometimes it pops up on standardized tests. Just understanding that odds is different than probability. Okay, you can kind of get the odds and then shift them around. Say 2 and 3 come together to be the 5, and that's how we get the denominator here. But odds are not the same exact thing as probability. All right, let's keep on moving on. So if we're looking at ratios, ratios a lot of times are used with like blueprints and scale models and stuff like that. So if we look at this problem right here, it says Peter's into making model airplanes. The last one he made had a wingspan of 12 inches. The actual plane it was modeling had a wingspan of 60 feet. What is the simplified ratio of wingspans of the model to the actual plane? Okay. Now some people would write it like this. 12 inches to 60 feet. Now, oftentimes that's okay. This would reduce to 1 over 5, and it would be inches to feet. But the problem here is this it's not the same unit. So if you're trying to talk about what the scale model was, like how much smaller, it's not actually 1/5 of the size. In order to actually look at what the scale would be, you would have to have the same exact units. So instead of saying 12 inches, I'd say 1 foot to 60 feet. And that would reduce to 1 over 60. Okay, it's good to have those units being the same. And now I can say Peter's plane is 1/60th scale model of the real thing. When you have it like this, is when you're looking at like a map or something and you're going to continue and you're going to write a proportion, but you're okay with the next one being inches over feet as well. When you're talking about a scale model or something like that, you want to have the same exact units. All right, now for another one. It says Mr. Gallagher is going on a candy binge. He is going to buy Heath bars, which were my favorites. Loved how the toffee got stuck in your teeth and you enjoyed it for a long time. Or Skittles. Didn't really enjoy Skittles that much. For some reason, they make water taste funny after you eat Skittles. Didn't notice that? Try it out, you'll see. Anyways, the ratio of Heath bars to Skittles is 2/3. If he is planning on buying 120 candies, how many of each kind will he buy? I'm going to show you 2 different ways to do this. One way would be saying 2 Heath bars to the total candies, which would be 5. 2 and 3 together make 5. And then you would say how many Heath bars if I'm going to put 120, or if I'm going to buy 120 candies altogether. At that point, you could solve and get 5x equals 240. And when you divide by 5 and divide by 5, you get your trusty calculator, and you say 240 divided by 5, and that gives you 48. Now that you know how many Heath bars, it's pretty easy to find out the Skittles, because you would just do the 120 and subtract away your 48, and that would give me 72 Skittles. Now you might be asking, Mr. Gallagher, I don't get it. How come you didn't say 2 over 3 equals x over 120? You got to be careful. This is Heath bars to Skittles and then Heath bars to total. So it would have to be Heath bars over total equals Heath bars over total. Okay? Or Heath bars over Skittles over Heath bars over Skittles. But since what they gave us was the total, we had to change this around a little bit. That's why I put the 5 down there rather than the 3. Now, a different way you guys can do this, which is my preferred way, if it says 2 to 3, you say 2x plus 3x equals 120. That gives me 5x equals 120. And when you solve 120 divided by 5, you get 24. Now you got to remember that's not your answer. What you would do then is substitute back in. 2 times 24 is 48. That's how many Heath bars? 3 times 24 is 72, and that would give you the number of Skittles. So if they give you this ratio, you could write, say it was 5 to 7, then you could say 5x plus 7x. You just need to remember to substitute back in. Okay, now I want you guys to try this problem. We're saying two angles are complementary. Remember that means 90 degrees together. Try to figure out what each one of the angles is going to be if they are complementary and the ratio is 2 to 3. You can do it however you want, either method 1 or method 2. All right, so we would want to say 2x plus 3x equals 90, because that's how I like to do it. It's the easier way. 5x equals 90, and x equals, I think it's 14 maybe? Nope, 18. Equals 18. And then we would just substitute back in. 2 times 18 is 36. One of the angles is 36. And 3 times 18 is 54. Now, a little reminder, in many different subjects, you can't check your answer. If you guess that the 5th president was Lincoln, I guess you can think if your answer is reasonable to see if that was the right time frame, but it's not like you can substitute it in and make sure it works. For us, we know they should add to be 90. So at the very least, for it to be reasonable, you should add those together and get 90, which we do. So we know our answer is reasonable, at least. If it was like a true just solving an equation, you could substitute back in and make sure it works. But for this, that might not be 2/3 or 2 to 3 ratio, but at least we know they add up to be 90. All right, we're cooking along. So an extended ratio, if we're looking at a normal ratio is going to be comparing two things. An extended ratio is going to be a way of comparing more than two things by division. So let's say we were talking about three things. Instead of me buying Heath bars and Skittles, it was Heath bars, Skittles, and another one that's great and gets stuck in your teeth, Butterfingers. And I would have to have three numbers. So the ratio might be 2 to 5 to 7 or something like that. So you'd have more than two things. The applications are a lot alike to what we just did, and you're about to see that in just a second. So, if your notes are out of order as well, but mine kind of jumped into a different section. So for mine, I had to keep flipping the pages until I got to this page that says the lengths of the sides of a triangle are 3 to 5 to 6. So go ahead and flip there and try to find that page if yours is messed up like mine. All right, so back to what we were talking about. Even though there's three numbers, we would do it the same. In this case, I would really highly recommend not doing it using method 1, because method 1 would have to be 3 over all of them together gives you 14, and you would set up a proportion, and then you would have 5 over 14 equals, it would just be a huge pain in the hiney. So let's go ahead and do it method 2 because that's quicker and easier. 3x plus 5x plus 6x equals the total perimeter, which is 196. That gives me 14x equals 196. And when I go over and solve that, I get 196 divided by 14 equals 14. So x equals 14. And you would have to substitute it back in to find out all the numbers. 14 times 3 is 42. One side must be 42. 5 times 14 is 70. And the last one is 6 times 14. That gives you 84. Ta-da! Okay, now I want you guys to try this one. It says that the ratio of Paul's pay to John's pay to Karen's pay is 1 to 4 to 5. The total is 180. Then what does each person get? Figure out what numbers. So you should have had 1x plus 4x plus 5x equals 180. That gives me 10x equals 180. X equals, when you solve that, you get 18. And when you substitute back in, 1 times 18 is 18. 4 times 18 is calculator time. 4 times 18 equals 72. 5 times 18 equals 90. And once again, if you want to check your answer, add them up and make sure that you get this number. Still aren't guaranteeing that it was a perfect 1 to 4 to 5, but most likely if they add up to 180, then you probably did the method right. Okay, now when we talk about proportions, we've kind of been using them here. A proportion is basically an equation, a true equation showing two fractions are equal. So let's say we had 1/2. If you wanted to think of a fraction that equals 1/2, 3/6. That is going to be a proportion right there. We know the left equals the right. 1/5 and 2/10. Okay. Now there's a special thing with proportions. If you know something is a proportion, you can cross multiply. That times that will always equal this times this. So 2 times 3 is 6, 1 times 6 is 6. This is actually a handy way. If you got a fraction that was like 32/90ths, is that equal to 1/3? You can cross multiply and see if it makes sense. 1 times 90 is 90, 3 times 32 is not 90. So those are not equal fractions. Now, most times when we do this, it has to do with us having a missing part. You'll have 1/5 equals x over 10, and you will use cross multiplication to figure out what that x needs to be. So in a proportion, the product of the means equals the extremes. Okay. I'm not going to make you guys memorize which one is means and which one is extremes because honestly, I forget every time. I would have to Google it right now to figure out, is it going down, which is the means, or is it going up, which is the means? So more importantly, if you're looking at this, just know that AD equals BC, meaning you can cross multiply. Okay. So let's keep on going. So if you're looking at something like this, Some people love to go over and just say, 6 times what number gives me 10, and do the same thing to the numerator. I don't like that. Um, it's much, in my mind, I like going like this. 5 times 10 is 50. 6 times x is 6x. And then you divide by 6 and divide by 6. And that would give you 25/3. Now, if you had something like this, 5 times 5 is 25, and 2 times x plus 3 equals 2x plus 6. Minus 6 minus 6, that gives you 19 equals 2x, and divide by 2. So what you needed to remember to do on this one was distribute. Okay, don't forget 2 goes to x and 2 goes to 3. Now on this one right here, x times 10 is 10x. 3 times x plus 7 is 3x plus 21. At this point, it's just algebra. You get 7x equals 21 and x equals 3. So don't forget to distribute. Now, there is one last thing here, and we're going to actually skip the properties of proportions. Take a look at this. This brings into the real algebra stuff. So if we go over and cross multiply in here, you would get, let me get the font to be smaller, x times x plus 5 is x squared plus 5x. Negative 2 times 3 equals negative 6. Now you're going to have to dig back into your time in Algebra 1 to remember how to solve a quadratic. One way is to graph it and look at your x-intercepts. Another way is the quadratic formula, and another way is solving by factoring. This is probably the quickest and easiest way. No matter how we're going to do it, you got to get one side equal to 0. So I'm going to add 6 and add 6. You get x squared plus 5x plus 6 equals 0. I'm going to factor. Let's see if you guys remember how to factor. Do you remember the ACB chart, where you had to find two numbers that multiply to get that and add to get this? What are two numbers that multiply to get 6 and add to get 5? And we'll do more of these in class too. It's 2 and 3. Since there was no number in front of x squared, we can jump straight to saying x squared plus 5x plus 6 is x plus 2 and x plus 3. What's the only way that something times something could equal 0? Well, either something number 1 equals 0 or something number 2 equals 0. That is how you solve by factoring. And lastly, you would just solve these small equations, one-step equations. X can be negative 2 and x can be negative 3. And the only last step would be substituting back in and making sure that they actually work. Okay, we will go over and do more of these since this video is running kind of long. We will do more of these problems where you have to solve by factoring when we meet as a class. Now, one last thing that I needed to show you. We don't use it very often, and we're not going to do any of these ones down here. But just make sure you guys understand when it comes to proportions, one of the things you can do is if you have A over B equals C over D, you are legally allowed to flip both of them. Feel free to flip both of them. The other thing you can do is do numerator over the numerator of the other one equals denominator over denominator of the other one. And then the last one is really weird. You can add the denominator to the numerator as long as you add the other one's denominator to its numerator. This only pops up in very few questions, so we're not going to spend much time on it, but it's important to know that you can flip the fractions. You can put numerator over numerator equals denominator over denominator, or you can add the denominator to one of the numerators as long as you add the other denominator to its numerator. All right, that lesson is getting a little long here. So once again, mostly just make sure you guys remember how to cross multiply. Don't forget to distribute. Know what a ratio is. And then in class, we will do more of these ones where you have to solve by factoring. Because no matter what class I teach, when I bring up factoring again, people pretend like they've never seen it before in their lives. Now, to be honest, you guys probably learned this when you were online last year at the end of the school year, but you still covered it in Algebra 1. Thank you so much for watching. Sorry that one ran a little bit long. Have a good one. See you in class.